So this webinar series is about water quality monitoring from NASA remote sensing measurements. And what we want to do today is this is an outline of the webinar today. This is the first session, so we will talk a little bit about this course. We will talk about the ARSET program, which offers this webinar, and then we will go on to water quality monitoring from different NASA satellites and sensors. So this is the order. So course information. The objective is to introduce remote sensing data, data access, analysis, and applications for water quality monitoring, especially in coastal oceans, inland lakes, and estuaries. Now, this course is really, it assumes that it's a beginning course, the first level course, so it really covers the basics of water quality as well as about remote sensing. And the course will focus on surface water quality more, not groundwater. We're just going to focus on surface water. And what this shows here, the maps are shown here is a water body, and satellite can give a nice continuous coverage of a water body, and a number of water quality parameters or properties can be derived. So that is what the webinar will focus on in next 3 weeks. So starting today, we will have 2 more sessions next Tuesday and then Tuesday after, November 25th and December 2nd. We have 3 different sessions in the sense that we are also offering this webinar at 8 in the morning, and we are offering it in Spanish as well at 10 in the morning. So this is to reach around the world, people, different time zones, different languages. So that's how we are offering this. There will be a homework assignment given after the second session, and all the participants who complete all 3 sessions, they attend all 3 sessions and complete the homework, they will be assigned a certificate of completion. Okay, so course outline content-wise is today we are just going to go over some introductory material about remote sensing basics and about water quality basics. Next week, then, we will focus on specific data sets from NASA satellites and how to access those data sets by using web tools. So that will be next week. And third week, then, we will have an overview of water quality monitoring, where the field is today and what the future is. And then we will have a couple of case studies of monitoring water quality in selected water bodies. So my name is Amita Mehta, and I am an instructor with ARSET for a number of years, and I focus on water resources and disaster management area. We have Africa Flores. She is from NASA's Surveyor program, and she helps us with the water quality webinar material, as well as she is a speaker for the Spanish webinar. Ana Prados is the manager of ARSET program, and she also helps us give webinars in Spanish. We will be very fortunate to have a guest speaker in last week. He's from EPA, or Environmental Protection Agency, Dr. Blake Schaefer, and he's going to give an overview of water quality from satellite-based observations. Our presentation URL is ARSET GSFC NASA Gov webinar, and all the presentations we make, they will be available from this site. Marina Martins is our helper. Any information that you need, please contact her. We want to acknowledge help of Brock Blevins from ARSET. He is right now helping us organizing this webinar. He's online managing this, and he helps in a lot of ways. David Barbato is our Spanish translator. He translates our webinars into Spanish language, and you will find them on our website as well. Kristen Lee from NASA Applied Sciences Water Resources Program, she has helped us a lot in and encouraged a lot in putting water quality webinar together. So with that, I want to spend some time talking about Applied Remote Sensing Training, or ARSET program. ARSET is a program of NASA Applied Sciences program. It's NASA Earth Science has research as well as applied sciences program, and ARSET is a capacity building program that is supported by applied sciences. So Earth Science and applied sciences especially, they are supporting these themes shown here. There are 8 themes: agriculture, air quality, climate, disaster management, ecological forecasting and land management, public health, water resources, and weather. And the boxes highlighted are the themes where ARSET has been conducting training since 2008. So more information about ARSET. The goal of ARSET is to increase utilization of NASA um, observational and modeling data. There is a lot of data, and we would like to introduce, and as much as it can be used for decision support for environmental applications, that is what the goal of ARSET is. We try to conduct online webinars like this one, and we also conduct hands-on courses for policymakers and environmental managers. Also modelers, other academics also can participate, and public and private sectors. And we train everyone and whoever is interested in environmental applications. We have given, our webinars are international in nature, and hands-on trainings also we conduct in US as well as internationally. Um, Throughout the year, we plan webinars on different themes, and our website has information about all the webinars upcoming, so that's where all the information can be found. Um, One thing is that this webinars, all the trainings are focused on, it believes that there's no requirement that remote sensing has to be known. Before that, there's no requirement. Is we start from the basics, and then we progress to advanced level courses if anyone wants it. The presentations, hands-on presentations are held in computer labs where internet's available. So participants actually do computer-based activity of data access, data analysis, visualization, and how to get these data into decision support tools as well. We also have workshop with GIS, how to get remote sensing data with GIS tools. Okay. And as shown here, there is a gradual learning approach in the sense that all the webinars are free. They are really very basic level, not too technical, but there is enough information to use this data for decision support. And then once the webinars are given, people who want advanced training or any for specific geographical region or specific tool or data, then that can be arranged. This could be again hands-on, basic or advanced training, but this requires that we have a computer lab and internet availability. And we have done several such hands-on trainings around the world as well as in the US. So these are the 4 programs we are focusing on right now. Health, which is an air quality, which started in 2008. And a number of trainings have been offered, the most number of trainings, because this is the program that started earliest. And it has trained more than 900 people so far. Water resources and flood monitoring started in 2011, and we have trained about 600 plus end users for this application. Land use, it started earlier this year, and a webinar actually is currently going on in this area, and that will go on. This is also a very popular topic for agricultural and ecological management. Lastly, we are going to start a train the trainer program in 2015. So this uh, course will be designed for um, anyone who has a number of people working with them or they want to use this data. So one person can learn it and teach in a bigger group, so or bigger community. So this is going to be starting in 2015. Also, there will be training available if anyone wants to develop effective presentations and exercises, especially using NASA remote sensing data. So this map gives an overview of the countries that ARSET has reached through webinars as well as hands-on trainings, and these are the states covered in the US, and one can see how many organizations are covered in each area. So we have almost everywhere in the US we have given trainings, and over the world also several countries we have reached. More than 1,800 end users have been reached during 2009 to 2013 time period. Okay. So these are some of the recent courses that we have done for water resources and flooding. We started with hands-on training in Cartagena, Colombia, then University of Oklahoma and the World Bank. Last year they had hosted a event and training in flood applications. A number of online courses. Information about these can be found on our website. Again, all the presentations are available as well. Earlier this year, we had a presentation and data demonstration at USAID Geo Center in Virginia here, looking at, again, water resources and disaster management. So this is about ARSET, and now this is ARSET website. So on ARSET website, this is the web address. All 4 themes that we provide training in are given here that can be accessed. And in this menu, there is a link for webinars, and that leads to all the webinars, current and past, and then by accessing these, all the presentations and recordings for some webinars can also be found. Similarly, workshops are also there. Hands-on training material can be found. Several case studies can be found too. And there is a apply for training link here. Anyone after taking webinars or after going through the material on the website wants to apply for a training or need more advanced training, they can apply through this link. Finally, there is a listserv that ARSET holds, and we send announcement of our webinars or other trainings, upcoming trainings through this. So if you haven't joined it, please join it so that you can stay up to date with ARSET. So with that, we want to start with today's agenda. Today is mostly introductory material about remote sensing as well as water monitoring, water quality monitoring. And so we will start with basic questions. What do we mean by water quality? Why is it important to know? Then we will move on to remote sensing of water quality parameters, what is involved in there, overview of remote sensing, advantages and limitations. Then we will look at a number of satellites and sensors available now and in recent past that they are monitoring water quality, they're used for monitoring water quality, and then a few examples of how these data are used in water quality monitoring. So to start with water quality, what we mean by water quality is it's a measure of the suitability of water for any particular use. So the properties that water holds, physical, chemical, and biological properties. Based on this, whether this water can be used for any particular use, that is decided. And so that is what we mean by water quality. Also, throughout this webinar session, we'll talk about parameters. And what we mean by that is it's a number of quantities. They define or describe water properties physical, chemical, or biological, and we talk about that. We call water quality parameters. Okay. So what are the properties and parameters? And so these are physical, chemical, and biological properties: color, temperature, density, heat capacity, turbidity, suspended sediments, pH, salinity, dissolved oxygen, conductivity, hardness, and biological properties such as phytoplankton or algal bloom, which are indicated by chlorophyll in the water, microorganisms, pathogens, or colored dissolved organic matter. All these properties define water quality. In the US, EPA, or the Environmental Protection Agency, is responsible for establishing water quality standards for different uses in different regions. And both EPA and USGS, US Geological Survey, they are quite involved in measurements and setting standard for water quality in the US. So how is water quality measured? Why is it important? First of all, it is critical for human and ecosystems health. Any water we find, we would think, is it safe for drinking or for swimming? Any water body we see, is it safe for aquatic life like streams, lakes, and coastal oceans? Is it safe for crop irrigation? So this is what we mean by water quality. Why is it important? Um, so water quality, what are the factors that impact water quality? So there are natural sources of water pollution, rainfall, snowmelt, runoff. Once there is rainfall and snowmelt, runoff can carry dissolved solids, other nutrients and chemicals into a stream or a water body. And eventually those streams can go to coastal oceans and pollute coastal oceans as well. So there are natural sources of pollution, as well as human sources are many, like urbanization, industrialization, farming, mining, fossil fuel burning, and sewage discharge, also animal waste, nutrient, chemicals, metals, pathogens. These are all resulting from human sources, human activities. And they're very important to know because as natural variability of climate as well as climate change due to other reasons, they all impact water quality in our streams and lakes and coastal oceans. Important thing to note here is that excess nutrients carried to streams, they can result in more algal growth, and they can lead to low oxygen because oxygen is used, and then that can be destructive or for aquatic life. And so this is one of the parameters that is effectively measured from remote sensing. So that's why it is highlighted here. So how do we measure water quality? So these parameters that we mentioned, some of them, most of them traditionally were measured or they were derived from in situ measurements. So water samples are collected from streams and even oceans, near coastal oceans, and in the lakes. So these water samples are then analyzed sometimes right there with help of some instruments, or they are taken to labs, and then lab analysis have to be performed to find out information about water quality parameters in water. Again, in the US, EPA, USGS, and NOAA, they're all involved in collecting samples and analyzing them to find out water quality, to monitor water quality. So there are some limitations to these in situ measurements. As shown here, this is Lake Erie, and red dots shown here are the places where water is sampled or water sample is collected and then analyzed. But as one can see, the lake is quite big, and these discrete points may not capture everything that is going on in this lake. So there's one limitation is about sampling. that it's not entirely representative of whole body. Then also how frequently these samples are collected. That also is an issue, that temporal coverage may not be enough to resolve or capture daily, monthly, or seasonal changes in water quality. Also, it's labor intensive. So water samples have to be collected and they have to be analyzed, and it is expensive as well. And even at the end, samples are limited. So these are some of the limitations of in situ measurements. That is not to, I mean, they're extremely important because they they are always used along with satellite measurements. So then the next step is to look at Earth observing satellites. They provide continuous coverage of spatial regions, and NASA has a number of missions flying for a number of years, so that there is also a evolution or change in water quality can be observed through these satellite measurements. So satellite measurements, they not all water properties or parameters are directly measured by satellite, but they can be derived. The color can be seen from satellite observations. Temperature, turbidity, and suspended sediment, these can be observed from satellites. Salinity also can be observed or derived from satellite measurements. Biological properties such as algal bloom and colored dissolved organic matter, these can be retrieved or derived from satellite measurements. So in addition to in situ, which is really very coarse in space, satellite can provide a large view of water quality in large water bodies, coastal oceans, and estuaries everywhere. So again, because of that, there's an example shown here, that this Gulf of Mexico, all the regions shown here in colors, that's where water sampling locations are. So this leaves almost entire ocean without sampling. But if you look at a satellite image, this was taken in 2011, October, from Aqua satellite, NASA's Aqua satellite, and this is the sensor MODIS that we will talk about subsequently today and in next sessions. It provides nice coverage of this entire region. So that is one thing, that it provides information where there is no surface-based information available. Okay? So it really augments in situ observations or measurements very well. There is global or near global coverage with satellites. So it's a large scale coverage, and this is quite useful when climate variability and change are observed in water quality. It's important to have a large perspective or a global perspective on it. Also, it provides continuous coverage and no point measurements, but it's a nice spatial coverage. So these are some of the advantages of remote sensing. So the objective here is to be able to use some of the remote sensing observations for water quality monitoring. And to do that, there are a number of things that we need to learn about remote sensing observations. And so we want to start with the basics. So what is remote sensing and how can we use it for water quality monitoring? So simply putting, remote sensing is just measuring quantity associated with any object without really touching it or without really being in direct touch with it. That's the basic definition of remote sensing. And the type of remote sensing or platforms used for remote sensing depends on the application for which remote sensing is used. For example, towers are used mounted with instruments to measure surface very high resolution. Local area are observed by these towers sometimes. Somewhat larger areas can be observed by aircraft carrying multiple instruments and taking remote measurements of surface and environment. And finally, satellites, they fly in space and provide near global coverage in most cases. So what one needs to know is which platform to use, what information to use, how much detail one needs, how frequently observations have to be made. These factors decide which source of data or remote sensing platform to use. Another thing to know about, in remote sensing or about satellite remote sensing is that what satellites measure. Satellites have a number of sensor or instruments they carry in space, and they measure properties of Earth and atmosphere from space by sensing radiation either reflected from Earth atmosphere system or emitted by Earth and atmosphere system. So a bottom part here that shows electromagnetic spectrum. This is a spectrum. It has these are different wavelengths. This is longer wavelength. This is shorter wavelength, as one can see, and 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 the and the frequency is given here, and wavelength in meters is given here. So any object with temperature emits electromagnetic radiation. And so this is the whole spectrum. Depending on what the temperature of the object is, radiation is emitted. So Earth atmosphere system emits radiation in infrared and microwave region, and it reflects sunlight incoming in visible and near infrared region. So this is the part of the electromagnetic spectrum used for satellite remote sensing. So most measurements done by satellite sensors are in this region. Okay. So again, talking about water quality measurement, they are mostly based on sensing reflected solar radiation back to space. So from any water body, incident solar radiation then is reflected back, and that is measured by satellite. So most sensors useful for monitoring water quality, they fall into the range of visible and near infrared light, which is the part of the solar spectrum. So using, as shown here, all the surfaces, they reflect sunlight, and then satellite measures. So water also reflects sunlight. So whatever is going on in the water, that changes the characteristics of how this reflection occurs. And based on that, information about water quality can be derived or retrieved for this particular body of water. And it can be done for any surface, but we're going to focus on water today. So most sensors, satellite sensors, we will be talking about will be using reflected solar radiation to detect water properties. And the water properties are listed here. Suspended sediments, algae, dissolved matter, organic matter, oils, plants. These alter energy spectra that are reflected back. And so they can be used to detect change in water quality. But there are also some chemicals and pathogens. They cannot really change energy spectrum or radiation spectrum of reflected light, or cannot change color of the water. Then these cannot be sensed directly from satellite measurements, but they have to be inferred from other water quality parameters. So there are a number of parameters which really can be observed from satellite. Okay. So there are two ways to generalize or categorize remote sensing technique for water quality retrieval or derivation. So qualitatively, looking at satellite images, changing colors can in different spectral bands, so different wavelengths which sense radiation, they change with changing water quality. So qualitatively, changing images or colors can provide some indication of change in water quality. More quantitative analysis or estimation of water quality parameters, they're based on algorithms, And these algorithms are derived statistically sometimes, most of the time, where satellite data are related to in situ measurements, and based on the statistical modeling or algorithm, then further use of satellite data is used to derive. And the example is shown here. This is again Lake Erie, and this is a true color image from MODIS that we will talk a lot about later. So this is just this is the image that satellite gets, and this is derived quantity. So suspended particulate matter is derived from this image. So just by looking at image also qualitatively, one can see that there is something different here than over this part. And when it is derived through a proper algorithm, one can find out that this color change is due to this suspended particulate matter. So this is just an example. And so these basically either images can be used, or sophisticated, more complex algorithms can be developed with multiple spectral bands and in situ measurements used in the algorithm. Okay, so with that in mind, there are certain basic features that one needs to know before using the satellite data. And that starts with sensors, satellite sensors themselves. So there are basically two types of sensors. Passive remote sensor, or that is just measures reflected or emitted radiation from Earth atmosphere system. And as shown here, MODIS is one sensor that is a passive sensor that measures reflected and emitted radiation from Earth atmosphere system. This energy now then is converted back to biogeophysical quantities such as temperature, precipitation, soil moisture, chlorophyll. So that is derived from what is measured here. And some examples that we will be looking at is from MODIS, from Landsat satellite. There is thematic mapper and enhanced thematic mapper. These are the sensors we'll be looking at. Other type of sensor is called active or active remote sensor, which is like a radar or LiDAR. And what these sensors do is actually they carry a source of radiation. They throw beams of radiation on a scene or Earth atmosphere scene and measure backscattered radiation. This radiation then is used to retrieve geophysical quantities. An example shown here is from shuttle radar topography mission from Space Shuttle. This radar was carried and it provides global terrain. This particular example is Mount Fuji, but terrain data again are used in water quality modeling because they route model to streams. So this is one of the data sets useful indirectly for water quality monitoring as well. Okay, so once we talked about sensors, now any data that we want to use for water quality measurements need to know spatial resolution, which is decided by, again, the sensor characteristics. It is smallest piece of Earth or atmosphere measured by a sensor is pixel. And so smallest pixel size is the highest spatial resolution a sensor can provide. Spatial coverage is simply the geographical area covered by a satellite. Temporal resolution is how frequently a satellite would observe same area of Earth. And temporal coverage is the lifespan of satellite mission. So that's the temporal coverage. So anytime we start using data, these are the remote sensing features that we want to see. So spatial resolution, again, it depends on the sensors, as we saw, and some examples are shown here. Landsat has thematic mapper and an enhanced thematic mapper, has resolution of 30 meters, which is pretty high looking from satellite. This is a Niger River Delta, and a lot of details can be seen over here. Next is MODIS, which is flying on 2 of NASA satellites, Terra and Aqua, and this is chlorophyll concentration. And what you see here is the resolution is 1 kilometer. So this is 30 meters, this is 1 kilometer, so this is much lower resolution and less details can be seen. There are other satellites, examples shown here. Tropical Rainfall Measuring Mission has and combined with other satellite provides rainfall at 25 kilometers. So it's a global coverage, but it's 25 kilometer. And then groundwater measured by GRACE satellite has even lower resolution, so it's 100 kilometer. So these are resolution varies with sensors. We will be working with Landsat. We were talking about Landsat data, which is 30 meters, and MODIS data, which ranges from this particular one is 1 kilometer. There are data available at high resolution as well. So we will be focusing on those. We want to talk about spatial coverage and temporal resolution. And both these, they depend on satellite orbital configuration. So there are types of orbits shown here. The leftmost is geostationary orbit. So in this configuration, satellite is flying about 36,000 kilometers above Earth. It is placed above equator. It goes around with the Earth and focuses on the same area of Earth all the time. So this can provide frequent measurements, but at the same time, it is not covering entire globe. Two other types of orbits are polar orbits and non-polar orbits. So polar orbits are where satellites goes around Earth from pole to pole. So it goes this side and then comes back. And these are circular orbits. They are moving. The satellite is moving as the Earth also rotates. And the height can be anywhere between 160 to 50 to 2,000 kilometers. And so this is polar orbiting satellite. Here there is non-polar orbiting satellite. So there is no coverage from pole to pole, although it covers all the longitudes. So this is non-polar orbit. So these orbits decide spatial coverage and temporal resolution. So polar orbiting satellites have almost global coverage. So these are typical orbits. Again, this is Aqua satellite showing Aqua satellite's orbits going from pole to pole. They provide information. Polar satellite passes over any area 1 or 2 times per day, depending on the geographical location. But then there are also some disadvantages in the sense that the swaths are quite broad. Also, there is orbital gaps in between. So some areas don't get observed every day or more than once. Sometimes non-polar orbiting satellites, they are even less than 1 per day. So they do cover global longitudes, but they also have orbital gaps. So depending on swath size, the spatial resolution and coverage can be decided. Geostationary satellite can provide multiple observations per day, but then they're observing only 1/3 of the globe at any one time, so there is no global coverage. So depending on the regional applications, data can be chosen from satellites. All 3 orbits are right now, satellites are there in all 3 orbits from NASA and NOAA. Okay, so we are going to talk mostly about these satellites for water quality parameter. And these satellites are in polar orbit, and so they are called sun synchronous because they measure radiation at the same time, AM and PM, every day at given location. So Aqua, Landsat, Terra, Earth Observing Satellite 1, and SUMI National Polar Orbiting Partnership satellites. These are the satellites. They have sensors on them. They are very useful for monitoring water quality. So that is what we'll be focusing on. So we've talked about all the orbits, but we're going to talk mostly about these polar orbiting satellites. There will be a future geostationary mission for water quality measurements that also we will look at in the next webinar or so. Some more information which is crucial, it is to know about spectral resolution and spectral bands of a sensor that we want to use for water quality monitoring. So spectral resolution, we looked at electromagnetic spectrum, how what part of that spectrum is sensed, how narrow the bands are or wide what is the width of these spectral channels. They they provide different information in different bands. So it is very important to know which part is a part of the electromagnetic spectrum is sensed, what are the channel characteristics, what the width are. Radiometric resolution is again how the data are stored, how the data are measured in terms and then stored in terms of digital numbers. So higher the number, larger this number, more accurate information, radiometric resolution can be there. And the sharper the imagery, larger the radiometric resolution. So these are some of the features that have to be kept in mind before using satellite data for any applications. These now shows examples of spectral bands for different instruments that we will be looking at data from in next 2 weeks. So this shows MORIS, CWEEPs, and MERIS. These are sensors flying on different satellites. And this is the wavelength in nanometer. So it shows that there are bands in different parts of the spectrum, and width also changes with sensor. And this information is very important to quantitatively derive water quality parameters. This particular spectrum here is chosen from ESTER instrument or sensor from Terra satellite. It has about 14 bands, and they have slightly higher resolution of 15 meter in certain region as well. One comparison shown here is these are Landsat bands shown in these bars, and this spectrum shown here is from a sensor called Hyperion flying on Earth observing satellite. So this has very narrow spectral channels. So just example of this band, Landsat would observe one value, whereas Hyperion will provide multiple values in this one wavelength band, and that can be exploited to get more accurate information or more information, different parameters from the scene that one is focusing on. So again, there are multispectral instruments. Some are hyperspectral. So these are multispectral instruments, and Hyperion shown here is a hyperspectral instrument. Okay, so this brings us to the satellites that we will be predominantly focusing on for data products. So Terra and Aqua, these are NASA satellites. They are carrying the moderate resolution imaging spectral radiometer or MODIS that we've been talking about. These data are readily available. They're derived from MODIS, chlorophyll concentration, temperature, color dissolved organic matter, turbidity, and euphotic depth. So euphotic depth is the depth in the water where light intensity falls, and that depends on a number of water quality parameters: phytoplankton, colored dissolved organic matter, suspended particulate matter. All these affect how deep light can penetrate inside a water body, and that depth is a measure that's known as euphotic depth, and that also is available from MODIS. Landsat satellite, which is one of the longest flying satellites and provides a number of sensors, TM, ETM, and operational land imaging. So spectral radiances or reflectance are available from these instruments. They can be converted to water quality parameters. Again, we talked about ESTER, which is the Advanced spaceborne thermal emission and reflection radiometer. This is also used for spectral reflectance and which can be used to derive water quality parameters, and also temperature is available, water temperature is available from ester. One of the recent satellites, National Polar Partnership or NPP, has a visible infrared imaging radiometer suite. So VIRS is continuation of MODIS in one way. These satellites, Terra and Aqua, have been flying since 2000 and 2002. We will see that in detail. NPP was launched in 2011, October of 2011. So this VIRS mission will continue for a number of years and sort of extend observations available from MODIS. So similar spectral bands are used in VIRS as well. And spectral reflectance and chlorophyll concentration are currently available from VIRS. So in next week's webinar, we will go through each satellite and sensor, characteristics of each sensor, and what data are available directly from some of the NASA websites, and then we will see how they can be obtained spectral reflectance that can be converted to water quality parameters. Okay, so these are additional missions. EO1 or Earth Observing Satellite 1 and these two. There is a sensor HYCO, which is hyperspectral images for coastal oceans. These are experimental missions or research missions. So data are available, but not they have to be requested. So we will talk about that, but they are hyperspectral and quite useful, but they are still research missions. There are recent past missions that we mentioned here, satellite SeaStar and NVSat from European Space Agency. So SeaStar had SeaWaves, which was sea viewing wide field of view sensor. This was designed to observe ocean color, so biogeochemical productivity in oceans, chlorophyll, temperature, inorganic carbon and organic carbon, and dissolved matter, all was observed through SeaWave. So this ended in 2010, but it is recent past. So looking at past data and current data from current satellite, one can see change occurring in any stream or coastal ocean region or any lake. So that's why these data are useful to look at history of what happened over a particular time period in some region. So we will briefly talk about those two. So we talked about a lot about remote sensing observations, and they have been very useful, but there are some limitations and trade-offs. We talked about spatial, temporal, coverage, resolution, spectral, and radiometric resolution. So it is very difficult to have everything very high spectral, spatial, temporal, radiometric resolution. As we saw an example, there could be multiple observations through geostationary satellite, but then it has limited spatial coverage. So that is one limitation. Another is that there are several sensors. They provide global coverage, and depending on what kind of orbit, which geographical region, there can be maybe 1 or 2 measurements per day for, say, especially for polar orbiting satellites. Higher spatial resolution data are available from Landsat and also from EO, about 30 meters or so. But then the swath width is such and the orbit is such that the revisit time is about 8 to 16 days. So there is less temporal coverage. Any of the sensors, first of all, they have large amount of data. They are stored in different formats. So this is one of the challenges of using this data, to get the data, pre-process it, and use it for any application. Then any satellite data usually needs validation, or for development of algorithm need additional data, such as in situ measurements are required. A lot of processing is required as well. So these are some of the trade-offs. Specifically for water quality parameters, their reflected radiance from water body passes through atmosphere. So atmospheric gases and aerosols, they also add to that reflected radiation. And similarly, if there are clouds, they dominate the scene of reflected measurements. So these have to be corrected before surface water properties can be retrieved. So this is a big challenge and a major part of retrieving water quality parameter from remote sensing measurements. There are the spectral bands that we have seen in say Landsat and MODIS. They are medium-sized spectral bands, and so they have combination effect of say chlorophyll or turbidity. A number of water quality parameters can contribute to that spectral energy. So to get the water quality parameters, again, sophisticated algorithms have to be developed. In coastal regions, depending on the spatial resolution, there is always in any pixel or footprint there can be a contribution from land uh, along with the ocean. So that has to be accounted for when water quality parameters are derived. So these are some of the things to keep in mind if data have to be processed to do water quality parameter. And so what we want to see now is just a couple of examples of how some of these data sets are used. Um, this image shown here is from ESTER on Terra satellite. And this is Mississippi Delta. And just looking at the image, one can see that there's a blue is water, blue and white is water, and red is vegetation. Or so as soon as you look at the image of the delta, it's clear that where water is polluted or where water has other substance in it that can be seen that changes the spectrum. So this is Terra ESTER image. Similarly, this is a Landsat 8 image. And what this is Lake Ontario, and closely looking at it, it shows the sedimentation pattern within the lake. And so just by looking at the image, it is easy to see that water quality or water property is changing within. And then this can be exploited to derive water quality parameters. This one case is, we will look at this case in detail in our last week, and this is a lake in Guatemala. This is also an ESTER image. This was 2009. It's a major algal bloom in Lake Atitan, and these green regions, the patterns show where the algal bloom was occurring. And again, blue is just the deep water shown here. So some of these sensors are very effectively used for looking especially at algal bloom or turbidity or suspended matter. This one case study that was done by a NASA Develop program. This is also a capacity building program, and link is provided here, and we encourage you to visit this site. This project used Landsat data and used in situ measurements of Secchi disk. This is a disk that is placed in the water, and when you don't see the disk, that's the depth to which the water is, say, it's the Secchi disk. It depends on transparency of water. So that was measured at these green dots, and then using Landsat data in bands 4, 3, and 2, relationship was derived to convert satellite radiances or to reflectances to this Secchi disk depth, and that is it's a nice. This is a typical way of doing water quality from remote sensing, that combining in situ measurements and looking at large area of satellite, you can convert satellite reflectances into some measurable parameter, water quality parameter. This example again here is from Landsat 7, and this is a lake in China, Hongse Lake, and this shows again chlorophyll concentration in milligram per cubic meter, and this also shows clearly where the chlorophyll and the scale is given here, how concentration is given. So it's derived again from Landsat measurements. Okay, and then this want to briefly show this site here. This is a NASA-funded water quality project, and this is to look at water quality into estuaries and coastal oceans. So this particular site, again, is provided by Gulf of Mexico Initiative Program, that is also NASA's Applied Sciences Capacity Building Program, and provides a nice visual information about water quality into a number of areas. So if you can bear with me for a few minutes, I want to show this site, that how satellite data are used to monitor water quality. And I will share my desktop with you. See this site, the web. So this is called a virtual buoy program. So number of number of information available, satellite data products themselves are available for a number of regions. But interesting thing is that this virtual buoy products. So suppose we focus on Suwannee River estuary and say there are a number of stations as shown in this map. There are a number of stations in the river estuary where in situ measurements are taken. So what this site does is at these stations, different parameters derived from MODIS satellite, they are provided at the same location. And so SST, so temperature is available, chlorophyll is available. This is light diffusivity coefficient, light penetration. Also, this is the these two coefficients are reflected of the dissolved matter, and this also is a how deep the light penetrates. So these are the available from MODIS Aqua, and picking at this is the station, and the information, suppose chlorophyll A, it provides at that particular station from 2000 when the MODIS started taking observations on Aqua satellite to present. These are monthly products in milligrams per cubic meter. Similarly, there are weekly products given here too. Long-term mean is given in blue, and then the trend is also noted at each station as given from MODIS data. So these MODIS data, of course, one can read detail in here. They are from, we will look at the site from which these data are obtained. These are global data, and from those global data, all these parameters are now posted or retrieved for extracted for particular stations, and then they are displayed here. So there are SSTs or temperature is shown, and this is monthly and this is weekly variation. At the same time, one can see how there is temperature is changing at this particular station in last several years, say, from weekly data, and these are just showing annual cycle and a small trend. So this is One example of how this is Florida Fish and Wildlife Conservation Commission. So these data are actually used for decision making in several regions. And so with that, I want to leave you with this presentation and we will go back to the presentation briefly. Okay, so this is the site again. It's worth exploring how different data sets are used for different applications and how visually information can be obtained. So this brings us to our next week's session. What we will do is talk about Terra, Aqua, Landsat, EO1, NPP satellites and sensors. We will talk about a few future missions, but mostly we will focus on tools to access some of the data sets that can be used for looking at water quality in particular region. So these are some of the tools that we will be looking at. And very briefly, we will also talk about models used for water quality monitoring. So combining observations, how models are used to either diagnose or sometimes even predict water quality. So that brings us to the end of this session. Thank you all for participating today. And if there are any questions, please type in the chat box so that I will try to answer some of those. And hope to see you next week, just about the same time. Okay. So are there any questions? Please type them so that do you have a site to retrieve? Yes. On our website, arset.gsfc.nasa.gov, the presentation is posted under water quality webinar. So all presentations will be posted also. Are there experiments with phosphorus and nitrogen? Now, for phosphorus and nitrogen, there are indirectly, you can look at algal bloom or how other planktons are growing in water. They are indicative of some of the nutrients, but there one has to use models to, because nutrients are coming from outside the water body in the water body. So they have to be modeled, and we'll talk briefly about that. Huh. So MODIS, remote sensing, accuracy of remote sensing, it's about 70% accurate, say MODIS. I'm talking about chlorophyll concentration. So, and as more hyperspectral instruments come about, and in future geostationary satellite is going to carry water quality sensing instrument, that will improve accuracy of water quality remote sensing. It is used along with in situ measurements. It has a lot more value. But again, there are data void reservoirs and coasts and streams where remote sensing will be very useful. Do you have any experience with remote sensing water quality in streams using high resolution imagery? As we saw, Landsat data, I mean, this is a research topic, and you will find a number of papers where streams are being looked, especially Landsat and Esther. They have now Hyperion. So there are papers which talk about remote sensing of streams. And we saw Mississippi Delta, where you can see, of course, there's a large region, but Landsat data have been used. Sorry about that. As you said, sensor. Electrical conductivity. I'm not aware of that, but I can check that for you. I'm not aware. I don't think so. Ah. Please, you can, if you can go online and apply for training. This is who to contact for train the trainer. Um, it is really more customized in the sense that if there is a trainer who is going to train a lot of people and wants to get information or training from us, then we work with them. So if you go on online ARSET, GSFC, NASA Gov, there is apply for training, and there this train the trainer can be, one can request that training. So again, the images are surface reflectances only, um, but surface up to certain depth, they are affected. Spectra are affected by how deep the say turbidity or suspended matter or they are. So, in combination with in situ data, the satellite images are used to derive this depth. So yes, that there you do need in situ data to develop these algorithms, and we will talk next time, and we will look at the CDAS, which there are algorithms that one can look at what they have done to get to different parameters. So combination of in situ measurements and satellite reflectances can be used together. Sometimes multiple bands and their band ratios are used to differentiate between different parameters. So it's specific sometimes with region and with the parameter that you want to measure. Is there some material we can study? There is a lot of, I mean, this is still a research area. I mean, new sensors are coming up, more and more information is coming up. So there is a lot of information to study. Um, which particular issue, please let us know by email and we can give you some material to read, or have you talked to someone who is already working in this area? Yeah, would you please give some guidance on best practice of how to collect in situ data for validating satellite data parameters? Um, that it is something that I think depending on the situation or like geographical region, what kind of water body depends on that. And I'm not an expert in situ data collection, but I can definitely put you in touch with people who do collect in situ data. So EPA, for example, they have they also have programs and guideline for how to collect water quality samples or how to do that. So USGS and EPA, these two are good sites to go to get this information, to get more information about how the in situ samples are collected, how they're analyzed. Yes, we will be briefly talking about hyperspectral sensor and how to get hyperspectral data. That also we will talk next time. This is about the question is about soil moisture. The SMAP mission will be most likely launched in January of 2015. It will be a polar orbiting satellite, so 1 to 2 times per day will be the temporal resolution. And temporal resolution will vary with sensor, but combined radar radiometer will be about 10 kilometers, I believe. And I will check on that. It is in that range. How important is remote sensing relating to water quality? If I'm not sure if I understand the question, um, but as we said, there are some advantages of using remote sensing data for water quality monitoring. Also, these data are actually completely free. Uh, One just has to learn to use the data. So if there are in situ measurements, it, it augments very well the satellite data because in situ measurements, they have limitations. And so that way, in my opinion, they are important. Yes, we will to look at MODIS images from this year to match some in situ data. Yes, we will talk about it next time. How to get um, basic spectral reflectances, or you want derived products from MODIS. That is what we will talk about. Yes, this is the link. And this presentation is already on our website, so you can look at the presentation and get the link as well. How are the water quality parameters validated? Yeah, basically they have to be compared with in situ measurements for validation. Also, um, I will confirm this, but there are aircraft-based measurements. Sometimes they are used for again comparing satellite derived data. But best practice is to use in situ data to at least validate some of the data for a particular region or water body. There's a question, how is it possible to detect groundwater from space? It is, there is a satellite, it's called GRACE satellite. And if you go on our website into water resources webinar, there's some information about groundwater. The resolution is a little coarse, but the data are available, yes, groundwater data. So if there are no more questions, we would end this session. You can always email us. Our email addresses are on our website also. If there is any particular um, data set or tool that is useful for any advanced training, please also let us know.